All right, so we're going to look at improper integrals. And there are two types of these. The first type that we're going to look at has bounds that are infinite. So has infinite bounds. And let's say, for example, that we look at the function, let's just look at y equals x squared. So the function y equals x squared, and let's say that we want to find the area under this curve from 0 to, say, infinity. So we would want to find the area under the curve from 0 to infinity. And if you look at this, then you can tell that obviously the area is going to be infinite. So there is going to be infinite area. There's no way that we could actually find a number to represent the area under that curve. These kind of integrals are easy to determine. So the integral for this one, it would look like the integral from 0 to infinity of x squared dx. So when we go to integrate that, we would integrate as normal. We'd get x cubed over 3. We'd want to evaluate it, and we want to evaluate it from 0. Infinity is not technically a number, and so we cannot technically plug that in. So you have to pick your favorite variable. I don't know why I like b, so I'm going to use a b. And then what we have to do is take a limit as b approaches infinity. So once again, you can't technically plug infinity in. You cannot write infinity once you write these bounds. Once you write these bounds that you want to evaluate the integral at. So each one of these is going to have a limit in there. All of these integrals have limits, and it is incorrect. It's sort of, I consider it to be grammatically incorrect to not put a limit sign in there. All right, so now we can plug in b and we plug in 0. We still have to take a limit. As b approaches infinity, I plug in b cubed over 3. I subtract and I plug in 0 over 3. That'll just go to 0. And now the limit as b approaches infinity of b cubed is infinite. And there's where we get that infinite area under the curve. We say that improper integrals, where you get that the limit of them, or that the area under the curve, so to speak, is infinite, we say that those are divergent. So this diverges. This integral diverges, and we get infinity. All right, let's do another example of this. All right, so let's do an example where we take the integral from negative infinity to 0 of x times e to the negative x squared. All right, so this is an integral that I want to use u substitution on. I'm going to choose u as negative x squared. So my du is negative 2x dx. So now in the integral, I have an x dx, and here I have an x dx. And for those, I'm going to substitute in negative 1/2 du. So again, I had my x dx, and that became, that 2 got divided, negative 1/2 du. Left in this integral is still an e, and negative x squared was u. Now I can integrate that. So I get negative 1/2 e to the u, because the integral of e to the u is e to the u. And I've got to plug it back in. So I'm going to plug back in u. I get negative 1/2 e to the negative x squared. Right, now I need to evaluate that from negative infinity, but I can't plug in negative infinity, and my favorite variable is b, so I'm going to take a limit as b approaches negative infinity, and my upper bound is 0. Okay, so I plug in 0. e to the 0 is 1, so I get negative 1/2. Then minus a negative 1/2. Sorry, just to be a little bit clearer, I got to keep that limit in there. I could have put the 1/2 outside of the limit, but so I'm plugging in b, so that's minus a negative. I still have this limit. I haven't evaluated the limit yet. As b goes to negative infinity of 1/2 e to the negative b squared. Okay, so now plugging in, so to speak, infinity into this. So I've got a negative infinity. Negative infinity squared would be a negative times negative, and that would be positive. So here's my thought process over here. I've got a negative infinity squared. That's something really big. Then I have still a negative out in front of that. So I still have a negative out in front of that square. And that would be the same thing as 1 over e to something really big. And when you've got something really big in the denominator, the whole thing goes to 0. So that means this entire piece goes to 0. And what we're left with then is just that negative 1/2 that was out in front of that. So there's the evaluation of this. And what this means is if we graphed this function, as it goes to negative infinity, it would get very, very close to the x-axis. And therefore we could find the area under that curve. So we can find the area under the curve. It's negative 1/2. And we say, when that happens, we say that this integral converges. So there's a couple terms for you: converges and diverges for these types of integrals. Okay, so we've only talked about the first type of integrals. These are easy to recognize because they'll have infinity in the bounds. Pretty easy. Second type. So the second type, the bounds contain, is what I'll say. The bounds contain a hole or I'll just say a discontinuity. So they have some kind of like a hole or a vertical asymptote, meaning that there's some domain issues within the bounds. Let's just look at an example. The integral from 0 to 1 of 1 over x squared. So when you look at this, x can't equal 0. We can't have division by 0. It's causing an issue. So we have to take a limit as our favorite variable approaches 0. We can't plug it in. It's technically, we have to take a limit as it approaches that discontinuity. Okay, so what we would do with this is that we would want to integrate it as normal, and in order to do that, I want to move that x up into the numerator, and that should just be I'm trying to find my eraser there, because that should just be a 2. X to the negative 2 when we move that up into the numerator. So then we add 1, and so that would be a negative 1, and then divide by that number. And so this is the same thing as negative 1 over x. Okay, so now dealing with the bounds. I've got negative 1 over x. I want to evaluate it. I can't plug in 0. So I'll use b, that's my favorite. And I'll take a limit as b approaches 0. And it does that, it approaches it from the positive side. And that's because the numbers that we care about in here are from 0 to 1. So because the numbers are from 0 to 1, they're numbers that are bigger than 0, and so we can go from the positive side. Okay, so we plug in 1, and we get negative 1. And then we've got this limit, so plus the limit as b approaches 0 from the positive. We're going to plug in b, and remember that this is a lower bound, so we've got minus that negative, so this is all positive, 1 over b. So now if we look at that limit, if we plug in 0, that whole limit would go to infinity. Any number over something very, very small goes to either positive or negative infinity. This is going to go to positive infinity. So this whole thing goes to positive infinity. We say it diverges. Okay, so now this is tricky. This is very, very tricky because, again, it's hard to recognize these. You look at this and you kind of think it's a pretty simple integral, but really there's a lot more to it. So now, on top of just even looking at an integral and figuring out how to integrate it, you also do need to do this little double check of the bounds. See if there's anything in those bounds that are causing issues. Let's do another one. So another example, let's do, say, the integral from 0 to 33 maybe, of x minus 1 to the negative 6/5. Okay, so now what's really tricky about this is that 33 doesn't cause any issues. There would be no division by 0. In 0, there's no division by 0. But there is an issue with 1. So with this, if we look at this, x minus 1 to the negative 6/5, that's the same thing as 1 over x minus 1 to the positive 6/5, and in that function, x can't equal 1. So this is really tricky. 1 is in between these bounds, and it's causing issues. And so what we really need to do is split this up into 2. The integral from 0 to 1 of x minus 1 to the negative 6/5. And then we've got to integrate from 1 to 33 of x minus 1 to the negative 6/5. And let me make sure I have a dx after both of those. Okay. All right, so I'm just going to concentrate on the first one first. So we have to add 1, x minus 1. If I add 1, I get negative 1/5, and then I would divide by negative 1/5, which would be the same thing as multiplying by negative 5. Then I would have to evaluate that from 0. 0 is okay, but 1 is causing issues, so I pick my favorite variable. And then I take a limit as that variable goes to, nope, not to infinity this time. So that is a limit as that variable goes to 1, and it's from the negative side. The negative side of 1, because we're looking at numbers that are less than 1 in those bounds. So I'm going to take a limit here. As b approaches 1 from the negative, I plug in b. So that's negative 5 times b minus 1 to the negative 1/5. Plug in 0. So minus, because I'm plugging in 0, a negative, that's going to make it positive. 5 times negative 1 to the negative 1/5. So now, if I plug in 1 from the negative side, so right in here, and I'm going to do this in a different color because this is kind of my thought process on this. So 1 minus 1 is equal to 0. And because of the negative 1/5, it's in a denominator. And because it's in a denominator, it is going to go to infinity. So on this first one, we actually get negative infinity. The negative comes from that negative out in front of 5. Now, I can stop at this point, because I know at this point that this integral diverges. I'm not going to find a number for it. Even though I haven't done this second part yet, I haven't done that at all, if one of them diverges, the whole thing is going to diverge. If you can't find the area under the curve from 0 to 1, if that's an infinite area from 0 to 1, well then the area from 0 to 33 is going to also be infinite. So if we had infinite area from 0 to 1, we're going to have infinite area from 0 to 33. So we are not going to look at this second one. So we don't evaluate because we don't have to. Okay, now if we had gotten this to converge, if we'd gotten a number here, then we would have had to evaluate the second one. Okay, so again, two different types. One are obvious, you've got infinite bounds, and the other type is not so obvious. You have to check for discontinuities, check for division by 0, or check to see if there might be a negative inside a natural log or a square root. Okay, so now, one other thing in these I'll look at, this is called the comparison test. I'm sorry, I want a different color. Comparison test for improper integrals. We can sometimes make conclusions about harder integrals if we know something about an easier one. So what the comparison test says is that we assume one function is bigger than the other. I'm just going to say f of x is bigger than g of x. Now, both of these functions also have to be greater than or equal to 0, and this only has to happen for x's that we care about. So I'm just going to say for x greater than or equal to a, where a is going to be some number. Now, there are two conclusions we can make. If the integral from a to infinity of f of x, if that converges, if that one converges, then the integral from a to infinity of g of x will converge. And the other one is if the integral from a to infinity of g of x, if that diverges, then the integral from a to infinity of f of x diverges. Okay, so some explanation here. If the integral from a to infinity of f of x, if we get an area under the curve of that function, so here's that function. So I don't know if I drew a graph. This is for the first one. So if I drew a graph of f of x, there it is. And I know that g of x is in between that and 0, so I don't know what g of x does, but it goes, I don't know, it goes like that. Who knows? All I know is that it's less than f of x. And all I really care about, now g of x can get bigger than f of x at some point, as long as it's always bigger from a over. All right, so then if I know that there is an area under the curve for f of x, so if the integral converges from a to infinity, so if I know that there's some area under that curve f of x, and obviously it's going to have to go to 0 eventually to make that happen, but if I know that there's an area under that, then if g of x is smaller, it has to have an area under it. Okay, so that says that if f of x is bigger than g of x and f of x converges, if we know an area for that one, then we would know an area under the curve for the smaller function. Now we can also do the opposite on this. If we know that g of x diverges, so if g of x is the smaller one and it has infinite area under the curve, then the bigger one would have to have infinite area under the curve as well. Okay, so let's do an example with us. So let's show, actually, no, I don't want to use that wording. let's use the integral from 0 to 1 of 1 over x squared. So let's figure out that one to see if the integral from 0 to 1 of e to the x over x squared dx, to see if that one converges or diverges. Right, now, earlier in this lecture, I think actually it was the first slide, we found that, so this is something we know, that the integral from 0 to 1 of 1 over x squared dx, we know that that diverges. Okay, so we know that that diverges. Now, we also know, if I look at the two different functions themselves, because we need an inequality in this, I could say, I would know that e to the x over x squared, that would be bigger than, or maybe equal to, and that's fine, 1 over x squared. And because of the e's and the x squareds, I know that all of these are greater than or equal to 0. Okay, so I have a correct inequality here, and now you might have to look back in your notes to see kind of how the theorem is laid out. But it says that if the smaller one diverges, so if the integral from a to infinity, in this case we have 0 to 1, and that's okay. If that diverges, and so we know that I'm sorry, I don't like the way that this is written out, of x to the negative 2, we know that that one diverges. So the smaller one diverges. If a function is bigger than that, then it also has to go to infinity. And so from this and from that theorem, we could conclude that the integral from 0 to 1 of e to the x over x squared, we could conclude that that diverges. Now I know on that theorem I listed those integrals from like a to infinity, and now I'm using 0 to 1. It still applies, because if you look at it bounded within certain regions, and as long as those discontinuities are happening at the same place, that's sort of important, that 0 is a discontinuity in both of these. Then you can make conclusions with other bounds. Okay, so I think that is it for this lesson.